All right, let's talk about valence bond theory and hybridization. So, valence bond theory and hybridization basically says, okay, so covalent bonds are formed by orbitals overlapping from individual atoms. Okay, so you have your 1s orbitals of hydrogen, they overlap, you get hydrogen. Okay, 1s orbital of hydrogen with a 2p orbital of fluorine, they overlap. Okay, I get hydrofluoric acid. Fluorine and fluorine, 2p orbitals overlap. Okay, great, fluorine, fluorine. So these bonds that are created by an orbital headlong overlap are called sigma bonds. Okay, we indicate with the lowercase sigma. Oop, hello, sigma. That's terrible sigma. Something like that. It's an O with a top hat. Okay. All right. The problem with this is orbitals don't have the right shapes. Okay. So, for instance, we know that our tetrahedral molecules all have bond angles of 109.5, but p orbitals, right, are on the x, y, and z axis, right? So, in order to get the right bond angles, we need to hybridize. And unhybridized orbitals form pi bonds, okay? Pi bonds, and those are your double and triple bonds, okay? So, let's look at this a little closer. So, hybridization itself is tied to the electron geometry, okay? So basically what you do is you decide, okay, I need this. So lone pairs go into hybrid orbitals and sigma bonds are hybrid orbitals, okay? So what you do is you take your orbitals and you hybridize them into equivalent orbitals. So I like to think of it as a blender. Okay, so I got my blender, and I'm going to take my S and my 3p orbitals. I'm going to throw them in my blender. I'm going to press the on button. It's going to blitz them all up, and what's going to pop out is going to pop out 4 equivalent orbitals. Okay, so I put in 1s and 3p, and I get 4 sp3 hybrid orbitals. So they're named after the orbitals that are blended. So if I'm doing sp hybridization, then I'm taking 1s and 1p, and I'm putting them in my blender, and it's spitting out 2 sp orbitals. And then I also have my 2 unhybridized p orbitals. Okay, sp2, same thing, but with 1s and 2p's, and then I have 1p left over. These are important. sp3, as we just said, we use 1s and 3p's. Now, and then if I want my expanded octet, well, I've run out of orbitals, so I need to get rid of my d orbitals. So sp3d and sp3d2 for my expanded octets. And these are tied to the electron geometry. So if you are linear electron geometry, you are sp hybridized. If you are sp2 hybridized, you are trigonal planar electron geometry. Okay? So you don't have to remember anything new. Just remember that, linear is sp, trigonal planar is sp2, tetrahedral is sp3, trigonal bipyramidal is sp3d, octahedral is sp3d2. Okay? So there's no tricks here. They are just directly tied to the electron geometry. Okay? And you need one hybrid orbital for each bonding pair and each lone pair. Okay? So our unbonded p orbitals form additional bonds like our double and triple bonds. So a double bond is 1 sigma 1 pi, a triple bond is 1 sigma 2 pi. Okay, so here's an example. Here's ethene. Okay, so it's carbon double bond carbon, 1 sigma bond, 1 pi bond. So you'll notice I have 1, 2, 3 sigma, so that's sp2, and then that extra p orbital, that's what's doing the pi bonding. Okay, so the sigma orbital is along the axis of the uh, the bond, and the pi orbital is shared above and below. And then if you were to do a triple bond, you do like around this, 90 degrees on the side. Okay, so let's go back and let's look at a couple of these. Okay, so let's think of a molecule. Let's do carbon dioxide. Okay, so that's got 2 electron domains, so I know it's going to be sp hybridized because it's linear. So this is 1 sigma bond and 1 pi bond. Okay, what about acetylene? Okay, this is 1 sigma. This one is 1 sigma and 2 pi. Technically, the sigma would be in the middle, but that doesn't matter. Okay, what about tin chloride? Okay, so I've got 1 sigma, 2 sigma plus 1 lone pair. That's 3 total hybrid orbitals I need, so it's sp2. As we just said, tetrahedral, so let's look at water. Okay, 2 sigma bonds and 2 lone pairs. So 4 total sp3 hybridized, and so on and so forth. So that's how hybridization works. Okay, so it's really just like an extra thing. So what you just need to remember is why is valence bond theory used? It's because we need the bond angles that we observe to work out. So because S's and P's don't have the right bond angles, we make hybrid orbitals that give us the right bond angles. And because lone pairs are part of the electron geometry, lone pairs go into hybrid orbitals. And because of this, the hybridization is directly tied to the electron geometry. The first bond, each first bond is a sigma bond, and then any additional bonds, a double bond or triple bond, would be a pi bond. So 1 pi bond for a double bond and 2 pi bonds for a triple bond.